Hey everybody, Trey here. Welcome back to another video. Quite the event across northern Illinois yesterday, as what was expected to be a very conditional and perhaps even marginal severe weather threat across the northern Illinois area quickly came together into the afternoon hours and turned into a localized tornado outbreak in and around the Chicago metro area. There were several photogenic tornadoes yesterday, including what was twins near the town of Elgin, Illinois. This is a close-up shot of the larger tornado there, lofting some debris. Just a very beautiful set of tornadoes there. And then a few that occurred in the Chicago city limits, including this one that moved very close to the O'Hare International Airport. So quite the event across northern Illinois yesterday, and I thought we would do a meteorological breakdown on this event while it's still fresh in everybody's minds. So without further ado, let's go ahead and get started. With the morning outlook yesterday, there was a very low-end, very conditional threat of severe storms yesterday afternoon across northern Illinois. As you can see, the northern edge of that slight risk and the attendant 2% tornado risk area barely extended up into the southern portions of the Chicago metro. And the reason was because we had an MCS that was moving into the enhanced risk area here, southern Iowa, northern Missouri, and eventually western Illinois. And we weren't sure whether or not we would see robust enough destabilization behind the morning line to support significant severe weather across northern Illinois yesterday afternoon and evening. But it became pretty apparent by the late morning hours into early afternoon that we were going to see enough destabilization behind the morning line, and I'll illustrate this in a second, to support robust severe weather across northern Illinois that afternoon and evening. By the midday outlook, the SBC nudged that slight risk northward just a tad, and it included a 5% tornado risk area from northern Illinois into northern Indiana, northwest Ohio, and far southern Michigan, and ingredients were coming together rapidly enough by the afternoon to support the addition of a small enhanced risk area across northern Illinois with an attendant 10% hatched tornado threat, including the Chicago metro area for the threat of a strong tornado or two yesterday afternoon and evening. As I had said, the morning MCS was a potential fly in the ointment for the afternoon severe threat across northern Illinois. Here is some radar imagery from yesterday morning. Well-defined bow echo here moving across Iowa, diving to the southeast across southern Iowa, northern Missouri, into western Illinois. And the question was whether or not we would see enough destabilization behind this morning line to support a robust severe threat in the afternoon. Well, you don't see any precipitation on the backside. This is about just after 1:30 p.m. Central Daylight Time. MCS very much weakening as it moves through the Chicago metro, and behind it, not much precipitation at all across Iowa into northwest Illinois. We can see that a little bit better on visible satellite imagery. Now, my normal source for my archived GOES satellite data, College of DuPage, unfortunately their archive cuts out just after 15Z, so we are going to have to use multiple sources to decipher our satellite data here, but we do have plenty of data that we can peruse for this case. So we start off in the morning, of course, strong MCS moving across Iowa, as evidenced by this very large cloud shield here and some of these stronger overshooting tops within the broader cloud shield. Outflow boundary extending out to the southwest as well, maybe some gravity waves in the low-level flow near that outflow boundary. The MCS continues on, and as we cut off our loop here, this is at just after 10 a.m. Central Daylight Time. You're already starting to see quite a bit of clearing on the backside of this MCS over Iowa. And then I did grab a screenshot from 17Z from the SPC Mesoanalysis page of the broader satellite view. Even more clearing at this point. This was about midday. MCS weakening here as it moves into north central Illinois. Plenty of clearing on the backside. And then as we go to our next source here, 1941Z, so just before 3 p.m. Central Daylight Time, this is eastern Iowa right here. This is Illinois. And you'll notice plenty of clearing across western Iowa into northwest Illinois at this point. The reason was because we had some drier air working in from the west. So behind that morning MCS, some drier air working in. This is the Davenport, Iowa sounding from 7 p.m. Central Daylight Time yesterday. So Davenport is right in here. Of course, Chicago right in there. So just pretty much due west of Chicago. And this sounding is evidence that we had some pretty significant dry air working its way in. And that drier air was helping to erode all that cloud cover and precipitation on the backside of the MCS and give us full, robust surface heating to increase that instability and allow robust convection to build. Of course, the red profile is our observed temperature as we go up in the atmosphere. The green profile is our dew point. Farther those are apart, the drier your air, and you can see above about 850 millibars or so, pretty dry air extending all the way up through the mid and upper levels of the column. That was helping to, again, evaporate all that cloud matter behind the morning MCS, leading to pretty robust surface heating and a nice reservoir of instability for the afternoon storms to tap into. That was a question in the morning as we saw that clearing on satellite really coming into play into the afternoon hours. The confidence in a more robust severe threat across northern Illinois began to increase pretty significantly. All right, let's dive into the meteorology behind this event. We'll start out at 500 millibars, as we always do. Very well-defined long wave trough centered basically across the eastern half of Canada into the northeastern quadrant of the U.S., with a well-defined shortwave trough rounding the southwestern flank of the larger scale system. Broad area of enhanced flow associated with that shortwave, 50 plus knots of flow there, and that shortwave would make its way to the east or east-southeast throughout much of the day. As you see here, associated with that belt of stronger flow. Very nice little shortwave there. This is at 3 p.m. Central Daylight Time. Very nice, well-defined shortwave with that belt of stronger flow associated with it. So that shortwave, of course, helped to promote a localized area of favorable ingredients, favorable lift, spin, etc. for severe weather across the region. Especially that northern Illinois corridor, and some colder air, of course, worked in, some cooling aloft worked in with this trough as well to aid in the destabilization behind the morning MCS, along with that abundant surface heating. Now, the trajectory of this shortwave, not going over any real major terrain features that would induce Lee cyclogenesis, so the surface pattern was a little bit, at least initially, on the more nebulous side. But we did see a weak surface low develop, weak but well-defined surface low develop across Iowa by about late morning or so. This is 16Z, so 11 a.m. Central Daylight Time. Nice, well-defined surface low here out across south-central Iowa. This would move off to the east throughout the day and provide a nice area of backed low-level winds with a somewhat of a warm frontal zone here as well. You see the wind shift, southerly winds to the south, more easterly or east-southeasterly winds to the north, so a warm frontal zone sat there with this surface low here. And this may have been associated with what we call an MCV, or mesoscale convective vortex. All an MCV is an area of spin left behind by an MCS, or squall line. So our morning squall line, our morning MCS, may have left behind an MCV. It's a little bit difficult to see on satellite imagery. Often you'll see it in a nice area of cyclonic or counterclockwise spin associated with an MCV. We didn't really see that on satellite data, but this surface low may have been associated with that MCV. It basically acts as an area of low pressure. And similar to a hurricane, out ahead in the northeast quadrant of an MCV, you can have a little bit of an enhancement of the low-level flow, and therefore a greater threat for tornadic supercells. So the track of the surface low slash MCV feature was here into northern Illinois. Out ahead of that, winds were nicely backed with this warm frontal zone right here that was lifting northward throughout the day as we got surface heating on both sides of that boundary, started to retreat north, and temperatures began to warm up into northeast Illinois, into the Chicago metro. So very nice, well-defined surface low here, perhaps part of the MCV. We'll take a look here at the vorticity, map of vorticity here across the region. Now, most of this vorticity, which is just spin in the atmosphere, and is often associated with these shortwave troughs like we have here. Nice maximum in vorticity right there. Some of this may have been influenced a little bit by the this MCV type feature, but just a broad area of spin in the atmosphere associated with the shortwave, perhaps a little bit to do with this MCV slash surface low feature moving to the east, but lots of spin in the atmosphere. The bottom line, lots of spin in the atmosphere, favorable for tornadic supercells. If we go to 850 millibars, we'll take a look at our low-level jet across the region. So again, weak low-level cyclone associated with that surface low just above that. Nice area of cyclonic curvature there with a very modest but moderate low-level jet out across northern Illinois. 30 to 40 knots out across this region. Out of the south-southwest, surface winds, as we saw, out of the south or southeast, especially north of that boundary, out of the east-southeast. So if you have those east-southeast surface winds with your low-level flow out of the southwest, that creates that very strong low-level shear favorable for tornadic supercells. And then with our west or west-northwesterly upper-level flow, that was able to create that strong deep layer shear favorable for supercells. So the kinematic environment across northern Illinois was definitely worthy of that 10% hash to upgrade. Very strong low-level shear, very strong deep layer shear favorable for tornadic supercells. The question was, how would the supercells react with the ongoing destabilization? And some of the behaviors that these storms displayed were very interesting with regard to how the atmosphere destabilized throughout the profile in the afternoon. We'll go through that here in just a second. Let's take a look at our surface data. This is at 13Z, so 8 a.m. Central Daylight Time. To start off the day, we had a nice reservoir of moisture out ahead and to the south of the track of the MCS. Some low to mid, even upper 60s dew points out across central Illinois, just sitting there. And the MCS expected to come through northern Illinois. These dew points just sitting there, ready to be advected northward post-MCS. So low-level moisture not an issue. You see some wonky winds out here across Iowa, and these R-looking symbols right there. That is a symbol for thunderstorms. That is our ongoing storm complex. Some westerly or northwesterly winds on the outflow of that storm complex. So that would move through across northern Illinois. And watch behind, though. So you'll take, for example, this station right here, that behind the MCS. Notice how rapid the recovery is behind the MCS. Starting at 72 degrees here at the surface at noon. We go on forward a couple hours. Just 2 hours later, we're already up to 80. So very rapid recovery of the low-level atmosphere behind the MCS. So again, that's why it was becoming so apparent and confidence was increasing in a significant severe weather event across northern Illinois yesterday afternoon. And by about 20Z or so, we really started to get a nice clean look at the surface profiles. Southerly winds across Illinois with those 60s and even 70s dew points now impinging into the northern Illinois vicinity, with more easterly or east-southeasterly winds here to the north. So a warm frontal zone, definitely somewhere in here, temperature gradient and wind shift somewhere in this vicinity. Again, that warm front was lifting northward slowly as we got surface heating on both sides. Now, I thought one possible saving grace for the Chicago area was going to be the fairly low surface temperatures to the north of the warm front. You see here at about 4 p.m., they are still hanging out in the low 70s. To the south of the boundary, they're into the low to almost mid 80s. So the temperatures on the north side of the boundary, a little bit on the cool side, and I thought that might increase the stability at the surface and perhaps allow the storms that would move into the Chicago area to struggle to remain surface-based, which would mean that their tornado threat would perhaps decrease as a result. Now you'll see that we do get some warming here as we go into the mid-afternoon hours. We get up to 75 here at ORD, which is the O'Hare Airport Station. So we did warm a little bit. Still, I thought we'd probably need to get into the upper 70s to low 80s to really tap into that significant tornado threat that was being forecast. We didn't end up getting there. We topped out at about 75, 74 there at 8 p.m. And it was a drop off from there. So we really didn't warm into that upper 70s, low 80s range across the entire Chicago metro. But it was enough, and oftentimes that is a saving grace for Chicago in many severe weather events. Some of this cooler air coming off of Lake Michigan moves inland and creates a little area of cooler air across the city, and storms that interact with that cooler air tend to weaken a little bit, and overall the tornado threat tends to decrease when that happens. I thought that might be a saving grace here, and I think it did end up playing at least a small role in the lack of significant tornadoes that we saw across the Chicago metro area. Of course, it didn't end up mattering all that much. We still got several tornadoes in this region, despite somewhat low surface temperatures. And of course, we've talked about before, strong low-level shear adds to the buoyancy in the environment. That can help overcome a little bit of low-level stability. And we had that low-level shear in spades. Of course, just to the north of the boundary, those winds out of the east-southeast with that low-level jet out of the south-southwest. That created some pretty impressive low-level shear profiles. This was the KLOT, so the National Weather Service radar in Chicago, the VWP, vertical wind profile, just after 3 p.m. Central Daylight Time, and you can see pretty impressive stuff here. Lots of curvature in that low-level photograph. 0 to 1 kilometer storm relative velocity, almost 500 meters squared per second squared. That is definitely well within the strong tornado range. And so that was helping to perhaps overcome that little bit of cool air at the surface. Of course, we were still getting heating to the north of that boundary. That warm front was retreating north. So all in all, it didn't end up mattering too much that those temperatures remained a little bit on the cool side. We still got a lot of tornadic activity out of that. And of course, the kinematic environment, the wind profiles, were certainly favorable for tornadic supercells. Storms began to fire on the west side of the Chicago metro by about 5 p.m. or so. You see the initial updrafts over here. Here's downtown Chicago right here. And just for some context, the town of Elgin, where those twin tornadoes occurred, is right in there, just south of the bend in this highway. So once again, initial updrafts occurred on the west side of Chicago here by about 5 p.m. or so and moved quickly off to the east, quickly attained supercell characteristics, took on that bean shape very, very quickly. That was thanks to the very strong deep layer and low-level shear in place across the Chicago metro area. And you'll notice as these storms moved into the Chicago area, they remained very much on the small side. And we'll talk about why as we go through our RAP proximity sounding analysis in just a minute. But some very interesting behaviors. Even though we were seeing strong destabilization, these storms remained very, very small, which was an interesting note with these storms. The storms off to the north and west also producing tornadoes at this point. As they passed through Elgin, of course, we saw the picture of the twins there. Continued to produce a few tornadoes as they moved off to the east. Again, some more supercell development across Chicago, some very nice, well-defined mini supercells, if you will, moving across the downtown Chicago area close to O'Hare. Then they would move off across Lake Michigan and then congeal into mostly a line as they moved off into the state of Michigan. They did produce a tornado in southern Michigan, but that was about it for the remainder of the night. Here's some velocity data to show you. And you'll see that we have, tough to see our couplet with the Metro Chicago storms, as there's a little bit of noise and range folding going on here. Again, we will show you some terminal Doppler radar data, which was situated much closer and gives us a much better picture at what these storms were experiencing and behaving like. But those storms to the northwest, you can see the couplets there with those storms, very strong rotational signatures in them. Of course, twins in progress at once, and we had a couple additional tornadoes as they moved off to the east into North Chicago. All right, let's take a look at a progression of RAP model soundings in close proximity to these tornadic supercells. I've chosen the location to be Chicago Midway Airport, so just south of the track of these supercells and very close to the one that moved very close to the O'Hare and Midway airports toward the downtown Chicago area. So we start off at 14Z, so 9 a.m. Central Daylight Time. Initially, very weak instability, and this might be a little bit deceiving. If we were to draw an actual parcel trace using the LCL height here, if you're not familiar with soundings, go ahead and check out my definitive guide to skew T's and hodograph series. I'll put a link in the description below so you can learn how to do this on your own. We find the LCL and do a parcel trace. You would get something that looks like this. So very minimal instability to start with, and that maintained through much of the day as that MCS went through, that cloud cover came through, and stifled destabilization for much of the day. But by about 18 to 19Z, so 1 to 2 p.m. or so, we started to see a little bit of an increase in the overall instability. A little bit of contamination here at 22Z, but 23Z was a very representative profile of the atmosphere. We'd fully destabilized by this point, about 1,500 joules per kilogram of mixed layer CAPE. So fully destabilized through the atmosphere. Temperature up to 77, dew point at 71, so a very moist low-level air mass. And take a look at that hodograph. That is a unit of a hodograph as far as tornadic activity goes. Very strong curvature there in the low levels of that hodograph, thanks to veering winds veering and strengthening winds in the lowest levels of the atmosphere. Strong low-level jet moving over the region as well, 40 to 45 knots there at 850 millibars. And very strong streamwise vorticity. We've talked about streamwise and crosswise vorticity before. Basically, you draw your storm relative wind vector from your storm motion vector to the level of the hodograph at which you're focused, and then your horizontal vorticity vector, which is perpendicular and to the left of the hodograph at that level. When those two vectors are parallel to each other, you have streamwise vorticity. You can think of streamwise vorticity as an NFL quarterback throwing a football with that perfect spiral. It's much easier for the wide receiver to catch. Well, same thing, if a supercell ingests streamwise vorticity, it's already oriented in the proper way, so the supercell doesn't have to do a lot of work to transform that into a tornado. So streamwise vorticity is much more favorable than crosswise vorticity in aiding in tornadogenesis in supercells. Crosswise vorticity is when these two vectors would be perpendicular. Then the supercell would have to orient that vorticity in the proper way before it can produce a tornado, which can make it a lot more difficult to get tornadoes with crosswise vorticity. Here you see a bunch of streamwise vorticity in the lowest levels of this hodograph, pretty much up through the entire lowest couple of kilometers of this hodograph. Let me do another one as an example here. Just almost purely streamwise vorticity through the lowest couple of kilometers of this hodograph, thanks to those very nice veering and strengthening winds with height. So a very favorable look kinematically for strong tornadoes. You can see that effective storm relative velocity also approaching 500 meters squared per second squared there. Very, very strong kinematic or wind profiles for significant tornadoes. But it became pretty apparent that the storms were not tapping into all this instability that was being shown on these proximity soundings. For example, the equilibrium level here, basically close to the top of your updraft. Of course, you can have overshooting tops that get higher than that, but where the atmosphere becomes stable, about 10 to 12 kilometers aloft. And it was clear that the storms were not growing to be that tall. They were very small, very shallow storms. And this is a little bit of video. It's a little bit tough to see here, but this doesn't look like all that robust of an updraft. These were as the storms were firing up on the in the western suburbs of Chicago. Not all that robust or tall of an updraft here. So it was clear that they were not tapping into all of this instability. They were storms were much shorter than what would be dictated, much shorter and smaller than what would be dictated on this sounding. So that brings into play that dry air that we talked about earlier. We showed the Davenport sounding from 0Z, 7 p.m. yesterday. That showed a lot of dry air aloft. And of course, as we said, that helped to destabilize the atmosphere, erode all that cloud cover behind the morning MCS, and initiate that strong surface heating and destabilization. On the flip side, that brings into play something that we call entrainment. And entrainment is basically when you have an updraft sucking in dry air from the environment. So if you've ever seen an updraft that looks really pinched off in the middle, you get really skinny, pinched off updrafts. That is due to entrainment. Dry air is getting sucked into this updraft. That dry air is evaporating all the cloud matter around there, and you'll get those really pinched off looking updrafts. Now, we still had quite a bit of instability here, and so those updrafts were not getting super pinched off, but entrainment was becoming a factor, and that goes to something that we call E-CAPE. Basically, entrainment CAPE. So your measure of instability impacted by entrainment. And there's a lot of folks doing some great work on E-CAPE now. We're in the very young stages of this new concept of E-CAPE. But basically, it's the instability that is decreased through dry air entrainment. And so this is just an estimate. But this, instead of this fully destabilized profile high up into the atmosphere, this profile probably actually looks something like this, where you had the dry air pinching off the CAPE in the mid to upper levels of the hodograph. So in turn, you get much smaller storms, as this would be the new sort of equilibrium level, similar estimate of the top of the storm, factoring in all that dry air. But you will notice that we still had quite a bit of low-level instability to deal with. On our main sounding here, 0 to 3 kilometer CAPE, about 100 joules per kilogram. So very strong low-level instability, and even with entrainment being factored in, we still had very strong instability in the low levels for these storms to tap into. And so even though the storms were very short and small, of course they're not growing that tall into the atmosphere because of this entrainment CAPE idea, they still were tapping into all of that low-level instability. If we look at our SPC mesoanalysis page, we'll start off with our cheat code. We've talked about this many times on the channel before, our surface vorticity and 0 to 3 kilometer CAPE, our tornado cheat code, if you will. So if we go into the afternoon hours, you'll see those blue contours, surface vorticity, moving in thanks to that surface low and MCV type feature there in eastern Iowa into northern Illinois. And throughout the afternoon, we had a nice increase in low-level instability, 125 to 150 joules per kilogram, moving into the Chicago area, coincident with that surface vorticity, that surface spin, that low-level instability. Even though the storms were a lot smaller than what they were perhaps expected to be, they were still able to, that low-level instability was able to really increase the ability for those storms to stretch that low-level spin into the vertical to aid in tornadogenesis. And that, coupled with the strong low-level shear, that was able to continue the tornado threat through northern Illinois, even though these storms may not have been as robust as they could have been. Also, mid-level lapse rates on the weaker side. We like to see them in that 7, 8, 9 degrees Celsius per kilometer range, really steep lapse rates in the mid-levels. That helps to really bolster the robustness of the updrafts. Sitting here right about 6 or even just below here in the mid-levels, you don't see that the steep leftward lean of that temperature profile there in the mid-levels that we like to see to really bolster that instability. So that may have also led to a decrease in the robustness of the updrafts, but still, we had quite a bit of instability. Really tucked in the lowest levels of the profile. So even though these storms were a lot smaller than they very well could have been, they were still able to tap into that very strong low-level instability and strong low-level shear and spin to create a few tornadoes across the Chicago metro area. Finally, here's some data from the terminal Doppler radar at O'Hare International Airport from yesterday evening. It's very rare to get a really good data set of a tornadic supercell from a terminal Doppler radar because terminal radars have a much shorter range than a typical National Weather Service radar. In other words, they can't shoot out nearly as far of a distance as a National Weather Service radar can. So a tornado or tornadic supercell has to be very close to the terminal Doppler radar in order to get a good data set. Well, we had that yesterday. We were very fortunate to get this supercell that moved toward downtown Chicago near the O'Hare and Midway airports to move very close to the O'Hare Doppler radar. So we'll start off here. You can see a very nice shape to the supercell, that flying eagle presentation. Very well-defined hook echo. It moved off to the northeast, and we actually were able to capture tornado genesis from this terminal Doppler radar here just near Burr Ridge. Very, very classic look to this supercell as it was producing a tornado. Here's the hook echo of the storm. This higher reflectivity area is where the tornado was, and here's your rear flank downdraft gust front. Very, very well defined on the terminal Doppler here, as you can see, very, very close to the terminal Doppler, which is located at that X right there. But a very classic look to this. The rear flank downdraft at the interface of that and the warm moist inflow is where you get your tornado right at the tip of the hook. And it did display some very interesting behaviors. Here is from the Midway terminal Doppler radar. This was put together by Cameron Nixon here. And you'll see some very, very interesting features here. I want you to pay attention to the tip of the hook echo. So here's our supercell. Here's the hook right there, and that this high reflectivity area is where the tornado is located. Some very interesting behaviors here. I'm going to let this play a couple times. Notice how almost immediately after the tornado first touches down, it occludes off to the northeast. So we'll go back here to the start. First tornado occurs. You start to see that on the Midway radar right there at the tip of the hook. Rear flank downdraft gust front right in there as well. But notice how quickly it moves off to the north or northeast. So it almost starts to occlude almost immediately as it right after it begins. And then by the end of the loop, you'll see that it almost detaches from the parent supercell. This is the updraft housing the tornado. It's almost cut off here. You see this blank space. Here's your supercell. Here's the updraft housing the tornado. So very, very interesting behaviors in that the tornado occludes almost immediately after it begins, moves off to the northeast, back into the rear flank of the storm, and then almost gets fully detached from the updraft. That gives you this look where the tornado almost looks like it's all by itself here. This is the updraft that is housing the tornado. Here's your tornado. And the parent supercell is way, way off this way. You see a little bit of the edge of the precipitation shield, but it is this updraft that's housing the tornado is way, way detached from the supercell. So a really fascinating look at the occlusion process going on here of this supercell. We're very fortunate to get a really, really good look at this occlusion process from the terminal Doppler radar. So that's going to do it for this video. Hopefully you learned a thing or two. Quite the interesting event yesterday, one that really came together in the last few hours before the event initiated, and just goes to show that you really have to look into the meteorology, into the observed data, to get a full sense of what's going on with the environment, as things like this can really ramp up in a matter of hours. And you can go from a very conditional threat to a full-on tornado outbreak with just a few tweaks of the environment. So with that, thanks for watching. We'll see you in the next video.